Welcome to our discussion of Ka, the ionization constant for weak acids. In this video, we will write an equilibrium equation for the dissociation of a weak acid, define Ka, and apply Ka mathematically. As we've discussed in our previous lessons, one of the ways to tell the difference between a strong acid and a weak acid is to look at the dissociation equation. A strong acid will dissociate completely and is therefore an irreversible reaction, whereas a weak acid will only partially dissociate, so it's a reversible reaction. And as we've also seen, when we have a reversible reaction, we can reach equilibrium, and therefore we'll have an equilibrium expression and an equilibrium constant for a reversible reaction. And that's exactly what Ka is. It's the ionization or the dissociation constant for weak acids. So let's take a look at what the equation for the dissociation of a weak acid looks like. So we're going to have HA, which is just a placeholder for any type of weak acid, plus liquid water gives us hydronium plus A. And A is going to be the conjugate base of our weak acid. So from this equation, we can derive our equilibrium expression as we've done with all of our previous equilibrium expressions. So our Ka is going to be equal to our products over our reactants. So in this case, it's going to be Ka equals the concentration of A times the concentration of hydronium over the concentration of HA. Notice we've left water out of the expression because it's a liquid. We can actually simplify this expression even further, because if we notice in our equation, our hydronium and our A concentration are always going to exist in the same ratios. So to simplify things, we can actually rewrite our Ka to be Ka equals our hydronium ion concentration squared over our concentration of HA. And do remember that our hydronium ion concentration is going to be the same as our hydrogen ion concentration. So we can even think of this Ka expression as our hydrogen ion concentration squared over our weak acid concentration. So a couple things to note about Ka. First of all, what is Ka used? Well, when we have the dissociation of a strong acid, we can very easily find the concentration of our hydrogen ions because we know that that acid is going to dissociate completely. It's a little trickier when it comes to weak acids that don't dissociate completely, and that is what we're going to use Ka for, to find the hydrogen ion concentration when not all of our acid dissociates. We can also use Ka to help us determine the strength of our weak acid. So the larger the Ka, the stronger our weak acid is going to be. Our weak acids are never going to be strong acids, but our weak acids can have varying degrees of strength while still being overall weak acids. So the more dissociation we have, the larger the numerator, means the larger the Ka and the stronger our weak acid. So let's take a look at some examples of how to apply Ka. So for our first example, what is the pH of a 0.5 molar solution of a weak acid with a Ka value of 8 times 10 to the negative 8? First of all, notice our Ka has no units because it's a ratio. Second of all, if we're looking for pH, then we need our H plus concentration, our hydrogen ion concentration. So we start by writing our Ka expression. And in this case, since we're after our hydrogen ion concentration, I recommend just writing the shorthand version of Ka equals your hydrogen ion concentration squared over your weak acid concentration. Then we plug in all of our known values, so we know that our Ka is equal to 8 times 10 to the negative 8, and we know that our weak acid concentration is 0.5 molar, and we're solving for our hydrogen ion concentration. And once we solve for x, we get 2 times 10 to the negative 4th molar. So that's equal to our hydrogen ion concentration. And then from there, we can go back to our toolbox. And if we plug in our hydrogen ion concentration to our pH equation of pH equals negative log of our hydrogen ion concentration, we'll find that we have a pH of 3.7. Now try this next example on your own. Pause the video, and when you're finished, hit play to check your answers. And there you go. For this example, all you need to do is plug in your concentration for your hydronium ions over your concentration for your weak acid, divide, and you get your Ka. Remember, when approaching these problems, it's important that you know the identities of your strong acids, because if it's not a strong acid you're dealing with, then it's got to be a weak acid, and your Ka will apply. And that concludes our discussion of Ka. Bring any questions you have with you to class.